So today's task is to continue talking about some basic differentiation theorems and the idea of rates of change. So we're going to talk about two different theorems, sine, cosine, and natural exponential function. Get on a little bit about rates of change, talk about velocity and speed. So the graph here depicts the sine function, and we want to think about, well, what is the derivative of this function going to be? Now we could work through the limit definition, and that's one way to do it. That's the way to know for sure it works. But instead I want to talk about how you can sort of believe and think about what the derivative of sine has to be. So the first thing to notice is that there are certain places, so at the top and bottom of each of these hills and valleys, where the derivative is going to be 0. We can see that the slope looks pretty 0 there. So we could fill in pretty quickly, or we could calculate that the slope will be 0 at all these points. Another thing to look at is the place where it crosses the axis here. It's hard to see here because my grid isn't square, but as it turns out here at negative pi, I have a slope of -1. Over here at 0, I have a slope of +1. And since the graph is periodic, I can make these marks at several other places where I know exactly what the slope is going to be. And now what I would have to do is I'd have to fill in the dots in between. If I just connected these dots right now, it might look kind of straight. But we can see that my slope in between, say, pi over 2 and pi, it's not straight, it's curving. It's gently changing from 0 to -1. And so what I would do is I would keep filling in the dots very carefully here until I end up with the following graph. And what I'm even going to do is I'm even going to replace this with a better looking graph drawn by the computer. Now hopefully, looking at this nice blue line, you can see what happened here. So we can say that the derivative of the sine function is going to have the exact same shape as that blue line, which hopefully you recognize as the cosine function. So as it turns out, the derivative of sine is cosine. Now what we can also do is we can also start by looking at the graph of cosine and trying to estimate what the derivative is going to be. So again, we look for common places right here at the tops and bottoms of all our hills and valleys. We know that the slope is going to be 0. So what we can do is we can go ahead and make marks of 0 there for the slope. And then once again in between, this kind of looks like sine function did before. So we can take a look here. Here it looks like we're going to have a slope of -1, +1, -1, +1. And we'll fill those spaces in. And so again, we've got this thing, and what we can guess is it's kind of going to be curvy here. So we can draw a nice curvy line in here. And what we're going to do is we're even going to have the computer draw that curvy line in so it looks a little bit more accurate. And hopefully what you see then is that the derivative of the function cosine of x is now going to be, it's not quite sine of x, okay? It's the negative of sine of x. This is sine of x flipped across the horizontal axis there, so it's not quite sine of x. So this is the key thing you have to remember. When you take the derivative of sine, you get cosine, but you have to remember that when you take the derivative of cosine, what's going to happen is you're going to get the negative of sine. So cosine starts out here at 0 by decreasing, which tells you you're going to get negative slopes, so that the decreasing matches up with the negative slopes. So that's how we get negative sine. So what we're going to look at here is we're going to look at the shapes of certain functions. And in red, what we have is we have an exponential function, 1.3 to the x. In blue, we have the graph of the derivative of the exponential function, which seems to match up because the exponential function is always increasing, so the blue function is always positive. And in orange, we have the tangent line at the point 0, 1. And we see that the slope right now is 0.26. So what we're going to do here is we're going to click and drag, and we're going to change our exponential function. So now it's 1.3, now it's 1.5, 1.6, 1.7, and we see that this is changing the shape of our graph, the red graph, as well as the shape of the derivative. And what we can see is if we start over here, it seems as if they're getting closer and closer together. If we jump way up high here, we can see they're sort of further apart. The blue function's a bit steeper now than the red one. But as we move back, they're getting closer. And so the question is, well, they seem to overlap somewhere in there. Well, where does this happen? Well, at 3, the blue graph has gone over the red graph. At 2.6, it's definitely in there. At 2.7, they look pretty close. So let's zoom in on this and see if we can see what happens closer in. So if we zoom in a little bit here, what we can see is that the blue line now at 2.65 is a little bit below. And as we scroll across, right around it looks like 2.71 is a pretty good approximation. 2.72 is pretty good. They're pretty much lined up right over each other. The derivative is equal to the function. The slope is 1. And so we want to think about, well, what number do we know that's pretty close to 2.71, 2.72? And as it turns out, this is the function e to the x. And this is why we use e to the x. When our function's e to the x, the derivative of e to the x is e to the x. So the thing about this is that it really is a neat function because the slope at any point is equal to the value of the function at that point. Now, one of the things someone could ask you is they could say, well, what's the slope of y equals e to the x at x equals 2? So you could go over to the graph and try to figure out, where the point 2 occurs, and it's going to be somewhere on our graph up around there. And you can figure out the tangent line, but the slope there, if you wanted to compute that thing, well, that's just going to be e to the 2. The slope at 2 is e to the 2. The slope at 3 is e to the 3. The slope at 4 is e to the 4. The slope at any number is going to be e at that number. That's what the derivative means. It means the derivative of e to the x, the slope at e to the x, is just e to the x. So let's take our new functions out for a spin and see what happens. Well, suppose we have the function given above and we want to compute its derivative. Well, then we just start as always. We say, well, we need to compute the derivative with respect to t of this whole thing. And the first thing, of course, to do is we break it up into its pieces. And once we have each of its pieces by the sum and difference theorem, what we can do is now we can look at each piece individually. So this piece has a constant here. Well, nothing wrong with a constant. That constant's going to come out. And so this first part is just going to be equal to 3 times whatever the derivative of sine of t is. This second part is not so bad. It's just going to be the derivative of cosine, which we just looked at a little bit earlier, is negative sine of t. Plus, well, again, we're going to pull a constant out, and then multiply by the derivative of e to the t, minus the one tricky one in the bunch. The t and the x don't match. This is just a constant, so we get 0. So now we can finish the problem by writing 3 times cosine of t, since it's the derivative of sine, plus the sine of t, plus 3 times e to the t. The derivative of e to the t is the greatest thing in the world because the derivative of e to the t with respect to t is just e to the t. It's really hard to get it wrong. So let's try one more example. Try to take the function, or the derivative of this function here, pause the video, and we'll see if we get the same idea. Well, as it turns out, we can't take the derivative of any part of this function so far. Our rules don't apply when there's something inside of sine, or when there's something more fancy as an exponent than just a t or a single variable. So this function we're stuck on, but keep waiting. We're going to learn some ways to handle these in the future. So now what we want to do is we want to discuss the idea of the derivative in terms of rates of change. So far we've been looking at derivatives and we've been saying slope a lot. We've been looking at the slope of a curve, but that's a pretty abstract idea. But a rate of change is a very practical idea. A derivative can be used to determine any time how much one variable changes in terms of another variable. So this is really the whole idea behind calculus, is trying to capture this idea of change, how things change, units of change. So anytime you have units that say something per something, that's pretty much a derivative. So applications, population growth. You can have people per year, people born per hour, In production rates, you can have units made per person, flows of a river, gallons per hour, gallons per second, velocity, acceleration, jerk. Anything per anything is a good time for a derivative. So anytime you're in a so-called practical application, which is fancy words for a story problem, what you want to do is you want to be looking for units. So if f is a differentiable function, then the units for the derivative of that function are going to be output units per input units. Let's look at an example of this. So suppose you're working on a problem and you have a function c of t, and it's a function that measures temperature in degrees Celsius. So this is your output units, and your input units are t, time, in hours. In order to find your units on your derivative, you need to take your output units per your input units. So in this case, we end up with degrees per hour. Let's try one more. So now suppose you have v of t, which measures your speed in feet per second as a function of t seconds. So again, what we want to be careful of here is that our output unit and our input unit get correctly identified. Our output unit is feet per second. It already is a rate, a derivative, a per. And our input unit is a function seconds. So then this means that our derivative v prime of t will be measuring things in feet per second. So there's two pers there. That's fine. We can put as many complicated things in there as we want. We just have to remember it's always going to be our output unit per our input unit. So one of the early uses of calculus was for measuring trajectories of cannonballs. So what would happen is you would have a cannon. This is a cannon. You would throw a cannonball inside of it. You would, light the fuse on the cannonball, or light the fuse on the cannon rather. It would go off, and hopefully you'd get a cannonball flying through the air, and it would land some distance away, okay? Now, the problem is this depends on a lot of things. First of all, you need to figure out, well, what angle did I measure it at? What's my current wind speed? Does it matter the weight of the cannonball? All of these things, well, how much gunpowder did you put in, right? The amount of powder. So there's all kinds of things that are involved in this calculation. And it used to be that people would just guess, basically. You'd throw some stuff in there. If your cannonball went too far, maybe put a little less gunpowder in it. If it went too short, throw in a little more. Who knows? Just throw it in there and see what happens. Well, that's a bad way to run a war. So what you want to do is you actually want to end up with some nice formulas that are capable of figuring this thing out for you. And what's really neat now is the military actually has really neat missile batteries here. So those are terrible looking missiles. But what this computer system does is it actually can measure based on, depending on the wind speed, depending on, the elevation of a target over here, where it is. What it can do is it can figure out exactly how to launch these projectiles, at what angle to launch them at, changing the angle here, so that it actually lands and hits correctly first shot. So doing the calculations is great because then you only have to take one shot, whereas before, you'd have to guess and check. Before we get to launching cannonballs, though, we need to start small, start simple. We're going to worry just about dropping stuff. So suppose that you decide that you're going to drop an object. Let s of t be the height of the function over time. So here, horizontally, we'll measure time. Vertically, we'll measure ourselves some height. We'll call it s. And our graph is going to look something like this. We're going to drop something up here from this height. It's going to fall to the ground. Okay, so this is ground level. Well, what we want to do is we want to figure out stuff like, well, how long does it take? How fast does it fall? Those kinds of things. So the first thing we need to figure out is our change in our height. So our change in height will be given by delta s. So suppose we picked a particular time here, and we decide we want to calculate, well, how fast are we moving there? That's going to be the tangent line. So in order to calculate this, first what we need to do is we need to calculate the difference from some little distance away. So delta t. So this vertically will be our change in s, our rise as it were. And so this delta t here we're measuring is going to be our small positive number. So with these two things, we can go ahead and we can compute what's going to be called our average velocity. So to figure out our average, it's just like before. We calculate the slope between these 2 points, our secant line, and we get delta S over delta T, and that's a good average. But I don't really care about averages. What I want to know is I want to know exactly how fast am I moving right up here at this point. And this means that the velocity right there at t is going to equal the limit as delta t approaches 0 of the change in our height divided by the change in time. So this means our actual velocity, without the prime there, just the velocity is going to equal the limit. Now in a few weeks we'll see actually how to figure out this formula for ourselves, but for now we're just going to get used to using it first. So you can actually figure out the height of a free-falling object using this formula. This is often given out in intro to physics courses. But the basic idea is that S of t is going to be your height, where we have to use the following quantities in order to figure out our height at any given time. So t is time, g will be the acceleration of gravity, v naught is your initial velocity, that is how fast you're going when you start out, S naught is your initial position, that is, did you start falling from 100 feet, did you start falling from 1,000 feet, 1,000,000 meters, whatever. Now, this does not include air resistance, so it is slightly off. It's a model, okay? It's a very, very excellent approximation to what happens, but it's not going to model everything very well. And also the key thing to note here is velocity is positive for objects moving upwards and negative for things moving downwards. Usually in everyday life we're not too careful and we just sort of talk about speed. You know, it's the absolute value of velocity, but it doesn't tell you direction. It's like if someone tells you in their car that they were going 15 miles per hour, well, I don't know if they're going 15 forwards or backwards. We sort of assume they're going forwards. Most people don't talk about how fast they back up, but if they really want to be careful, they could say they're moving at negative 15 miles an hour or 15 miles per hour in reverse. Okay? Do not say negative 15 miles per hour in reverse, because if you think about it, if you're moving negative 15 miles per hour in reverse, that's the same as moving 15 miles per hour forward. Think about this one for a little bit. I'm sure you'll get it. But right now what we want to do is we want to make use of this formula and see how we can use this to help us solve some problems. So here we have a very typical problem. A ball is dropped from 200 feet. Its height at time t is given by h of t is equal to negative 16t squared plus 200 using the formula from previously, where t is measured in seconds. A very typical question is how fast is the ball moving after 1 second? And so what you might say is, oh, well, this isn't so bad, you know. Let's see, the velocity after 1 second is, well, I bust out my limit definition here. Limit as delta t approaches 0 of my head at 1 plus delta t minus h of 1 all over delta t equals, but, well, what is this thing? This is the derivative at 1, okay? So this means I don't have to work through my limit definition. I know how to compute the derivative of this function a lot easier now. So that's what I'm going to do instead. Instead, I'll just compute, well, let's compute my derivative quickly here of h of t. So this will be the derivative of negative 16t squared plus 200. And so the derivative, let's see. So this is going to be a nice, let's see. I've got my constant negative 16 times using the power rule. I get 2t to the first plus 0. So I get negative 32 times t. All right. So this means now to figure out h prime at 1, negative 32 times 1 equals negative 32 feet per second. And so this is my velocity. Not too bad, since I know a lot of the good rules that can help me figure out these things. But let's do a little bit more interesting problem next. So a much more interesting problem is the following. Suppose that you drop a penny from the top of a building and it takes 8 seconds to land. How tall is the building in meters? When you want to use the fact that acceleration of gravity is negative 9.8 meters per second per second. Okay, so let's think about this. We had our formula from before that gives our position in terms of gravity, time, initial velocity and our starting height, well, what do we know? Gravity is going to be negative 9.8 meters per second squared, meters per second per second. My initial velocity, I don't know that. My initial height, I don't know that. It doesn't tell me. So whenever something doesn't tell you something, you got to think about it. Well, I'm probably not going to be finding or figuring out my initial height because that's what I want to figure out. But there's something important that happened in the problem that tells me my initial velocity actually. So take a second to go and look for it. So hopefully as we were reading along, you picked up on the keyword that you dropped the penny. Now if you're going to drop something, that means its initial velocity here is 0. So we actually do have a fair amount of things we can fill into our formula here. So this tells me that my original formula now is going to be negative 4.9 t squared plus 0 times t plus the height I want to figure out. The next step is to think about, well, how am I going to figure this out now? I want to know, I know I had 8 seconds to land, but I don't really know anything else. Well, I can always draw a picture of the situation. Okay, so I got myself a building here, right? And we'll just put this along the t and s of t axes. I threw that penny off, it went on down, and I know that after 8 seconds it hit the ground. So what this actually tells me is something really important about my function, that after 8 seconds it equals 0. So I know that if I put 8 into my function, it's going to hit the 0, because this means I hit the ground. So this means s of 8 will be equal to negative 4.9 times 8 squared plus my original height. So now I can figure out, using a little bit of algebra, that my initial height is going to be 4.9 times 8 squared, which just happens to equal 313.6. Now a question to ask yourself is, am I done? Let's see, it said, how tall is the building in meters? And I got myself a number down here, but I've forgotten something very important. I need to label my answer meters. Yes, labels are important. Always label everything. Okay, so one more thing to talk about. So as always, there are a few problems on Blackboard for you to try, and you should of course do the quiz, and of course you should post a question. But also you have one more thing to do for tomorrow. You need to run the following experiment. What you need to do is you need to get yourself a friend, a timer, and an object you can safely throw up into the air and go outside. Yep, outside. You're going to throw the object into the air pretty much straight up as much as you can, and make sure you're a place that you can do this. You want your friend to record the time from when you release the object to the time it hits the ground. Okay? Record this as accurately as possible. Your phone probably has a timer app, 2 decimal places, that'll be great. Also record the height that you release the object from, because you have to find the following. Use the position formula we were just talking about to determine 2 things. First, how fast you threw the object. And once you found out how fast you threw the object, I want you to record how high you threw the object. So you're going to want to work on both of these for tomorrow. Now there's a couple things that'll probably help you out here. First of all, remember that gravity is going to be negative 32 feet per second, or you can of course use meters as well if you prefer meters. Negative 9.8 meters per second squared. You know the initial height because you measured it. You know a length of time. So think about what's something special that happened at this time, and what is the height of the object at this time. And also think about when the object is at its highest point, how fast is it moving? Thinking about these questions should help you answer the other questions. But as always, we'll go over this in class, but you need to make a good try at it so that you can practice your thinking skills. But if you have any questions, please let me know.